Welcome to Lesson 2E, Toxicology. We're going to talk about toxicology. This is going to be mostly qualitative. There's just a lot of terminology. Let's talk about something called hypoxia first. This is due to an inadequate supply of oxygen. Normal air has around 20% oxygen. If you have less oxygen than that, you can start getting some problems. There's a real good example in the book that I'm not going to go through in detail. You can read on your own. This is in a submarine. So any closed container, like a submarine here, if you have some people in there and they're breathing, of course, so you have O2, you have nitrogen, and you have CO2 and some other trace gases in there. And they have something called an oxygenator that keeps the oxygen level safe. But what happens is, as you keep breathing, if that oxygenator is broken, the O2 will deplete and the CO2 will go up. So some people would call this CO2 poisoning. But CO2 itself is very non-toxic except very high concentrations. It can do some stuff to your blood that we talk about in the book. But really what happens in a case like this is hypoxia, where you can suffer ill effects or even die from the lack of oxygen. So it's not the CO2 that's hurting you, it's the lack of oxygen. Because when you breathe, you convert some of the O2 into CO2, and then you breathe out more CO2 than you breathe in, and you breathe out less O2 than you breathe in. So you slowly do this. Another good example is Apollo 13. Some of you have seen the movie. I lived through that era and remember this. They were in a capsule with 3 guys in there, and the same thing was happening in there. They had an inadequate source of oxygen for all 3 people in this little module. It wasn't intended for that. Apollo 13 was a launch that when they got to the moon and then they had some problems and an explosion. Watch the movie if you're interested. But they did survive. That's the good news. But they were almost ready to die from this hypoxia. In section 2.4, you can read about other diseases of the lung. This is, again, mostly qualitative. Section 2.5, sick building syndrome, or SBS. And this is a problem. This happens when you have bad air in buildings. And when I say bad air, this is usually due to poor ventilation. So later on, we'll talk about ventilation in detail, and we'll talk about number of room air exchanges. So the volume of the room, how many times per hour does that room air exchange? And if that's too small, you can have problems. A good example of that is cruise ships. They're well known to have poor ventilation systems on the cruise ships, and there have been several cases in the news, if you follow, in the past many years, where diseases, flus, and a coronavirus now, and other things have broken out on cruise ships, and when someone gets it, it spreads through to the rest of the ship. Another example these days, coronavirus, and as I write this in middle of August, 2020, we're finding, this makes sense, that it spreads most rapidly in crowded rooms, bars and restaurants. If you have too many people in there and poor ventilation, that's a recipe for spreading the coronavirus pretty rapidly. So that's why I'd much rather be outside than inside, especially if there's a lot of people in a room. And now they're telling schools and stuff to open windows, turn on their ventilation fans as high as possible, and mix everything up, and also to keep social distancing. So that's why, one of the reasons why. Section 2.6 deals with bioaerosols. So let's split up this word. Bio, of course, means biological, so there's something that has to do with life. Then aerosols is particles suspended in the air. So you heard of aerosol particles. Well, when particles are suspended in the air, that's called a bioaerosol. So for example, we have viruses. So coronavirus is a bioaerosol when it's floating around in the room. You have bacteria, you have molds, and other bioaerosols. Coronavirus is an interesting one in the news, of course, all the time. When people cough and sneeze, you get these small water droplets. Some of them are big. The big ones settle real fast, and the little tiny ones just move around with the air and stay in the air for a very long time. And all these particles, these droplets of water, contain within them the virus. That's part of the problem of bioaerosols. There's various diseases that are described, especially ones that affect the lungs. So again, this is going to be mostly qualitative. Section 2.7 is dose response. characteristics. I'm going to talk about dose response in detail in the next module, and body burden is something that we'll talk about. For now, I want to highlight two things: carbon monoxide poisoning and something called the Ehrlich index. And so I'll describe these in detail. So let's first look at carbon monoxide. And I'm not talking about CO2, carbon dioxide. This is CO, one oxygen instead of two. So carbon monoxide, just a comment here, when I teach my outdoor air quality course, outdoor air pollution, I mentioned that some politicians don't know the difference between carbon monoxide and carbon dioxide. CO2 is a greenhouse gas. The problem with CO2 that people are concerned about is global warming, but CO is a toxin. CO2 is not. As I said before, in very high quantities. The quantity of CO2 in the atmosphere is harmless for our bodies. The only concern is global warming. The problem with carbon monoxide is that there's hemoglobin, part of the blood cells that make blood red. What these hemoglobin molecules do is they absorb oxygen in the lungs and then they carry it to the rest of the body. So that's what happens normally. And so it works fine. And there's a problem though, when you have CO, is that hemoglobin absorbs CO more readily than O2. So if you have CO in the air, the hemoglobin is going to absorb that CO and send that through the body, and you won't have as much O2 going through the body. It turns out that CO is dangerous to breathe, and it's kind of like CO2. It's not necessarily harmful in itself. It doesn't cause problems in your body by the CO being there, but it deprives the body of oxygen. So just like we talked about Apollo 13 or people in submarines, CO2, if there's too much CO2, you have too little oxygen. And same thing with CO. If you have too much CO, you have too little oxygen. That's what causes the problem. When I say it's dangerous or hazardous, in small doses, it can cause headaches, and then if you have more, it can cause vomiting, and then you get weak, and eventually you can die from it. Lots of stories in the news of people using stoves or burning something inside without proper ventilation, and some of that CO comes out and leads to high enough levels that you have some serious issues. There's a plot in the book of the human response to CO poisoning, so I wanted to look at this quickly. Here's exposure in hours on a log scale, and then the percent of this carboxy hemoglobin, which is what I talked about, hemoglobin that has latched onto carbon monoxide instead of oxygen. So let's look at these different levels. These are in parts per million, so 15, 30, 100. So if you have low levels of CO, up to about 100 ppm, it's really no problem with toxicity of it. Once you start getting up to 300 ppm, you'll have a throbbing headache and maybe some vomiting, but you have to be exposed for a certain time and certain levels. So for 1 hour, for example, let's look at the 600 ppm. This is the 600 ppm curve. So if you're exposed to even 600 ppm for less than an hour, it's not really any problem until you get up to about an hour, and then you have a headache, reduced mental acuity, so you can't think straight. If you're exposed for, say, 10 hours here, then you're in serious trouble because you start to vomit and may collapse at a few hours. If it's all night or 10 hours, you'll fall into a coma and eventually can lead to death. Anything above 600 parts per million would have a curve that would be even further up here, and you could lead to death in a matter of a couple hours. So the takeaway here is that the amount of CO depends on two things: on the concentration, that's the ppm, these curves, and the duration of exposure. And those combined are what we call dose. A small ppm for a long time can be as bad as a big ppm for a short time. So that's how carbon monoxide can kill you. Finally, I want to talk about the Ehrlich index. This is really kind of cool. I don't see it being used too often, but it's a very useful tool for examining medicines and comparing different kinds of medicines. These are typical S curves that you see here. These are log scales. So here's dose on a log scale, and here's the cumulative distribution of some kind of chemical, whether you're breathing it or injecting it or eating it, whatever. You can use this for any of those types of ways of getting the drug into your body. So the Ehrlich index index is an interesting parameter. There's two curves, a curative curve and a toxic curve. So let me put the curative stuff in blue. This is 5%. So if this is a drug, say it's aspirin or it's some asthma medication, well, at this particular dose, we call this the 5% curative. 5% of the people are cured. If we keep giving a higher dose, we eventually, if it's a very good drug, so say you have a headache and you're taking aspirin and a little baby aspirin doesn't help you, it might help 5% of the people, but 2 or 3 aspirins, 4 aspirins will probably help most people. So we would call this 95% cure. But there's a problem. If you keep taking more and more aspirins, if you take half of the bottle, there's a certain dose, and I'll use red for the death ones. So this would be 5% toxic. And toxic typically with this can mean death, but it also can mean causing cancer or other things. So let's talk about death. If you take a half a bottle of aspirin, maybe 5% of the people would die. And then if you keep taking more and more, they eventually reach a 95% toxic. So 95% of the people die at some dose, and I don't know what that is for aspirin, but it might be 2 bottles of aspirin or something like that. There's these S-curves between them. And the Ehrlich index is simply the difference between the 5% toxic and the 95% curative on the horizontal scale. So let's make a little equation here. So we have the Ehrlich index, or EI, and that's equal to the dose for 5% toxic minus the dose for 95% curative. That's the definition of the Ehrlich index as indicated here on the plot, just the distance between those two.
I would think that you'd want the Ehrlich index to be as high as possible.
Ah, good observation, BJ. The bigger the Ehrlich index, better, for obvious reasons. You don't want the toxic curve to be down here, for example, so that the 95%, if the Ehrlich index is 0, that means when 95% are cured, 5% are dying from it. So that's not what you want. You want these curves to be far apart. So let's just discuss something in the news. Of course, the coronavirus. People are looking for a cure. And if you compare 2 different cures, suppose some drug companies come up with a cure for it, it will have an Ehrlich index. So if you take too much of it, people would die. And if you take too little of it, nothing will happen. And hopefully they can find one that has a very large Ehrlich index so that you can cure 95% of the people without hurting anyone. And the 5% toxicity level would be a lot higher. You'd have to take a really large dose, which nobody would take, and so that wouldn't hurt anybody.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.